Hello and welcome to this presentation about randomized message interception smoothing, where I will present our gray box certificates for graph neural networks. My name is Scholten and I'm with the Data Analytics and Machine Learning group at the Technical University of Munich. Before we dive into the details, let's quickly motivate the problem. We know that graph neural networks are susceptible to adversarial examples. To this end, robustness certificates provide provable guarantees for stable predictions under adversarial attacks. However, there are only two types of certificates for graph neural networks. On the one hand, white box certificates can certify specific models, but once we introduce new architectures, we will have to derive such certificates from scratch. On the other hand, black box certificates are model agnostic, but they also ignore important properties about the underlying classifier. As a solution, we propose gray box certificates that exploit the underlying message passing principles of graph neural networks. This allows us to certify robustness against strong adversaries that control multiple nodes in the graph and perturb node features by an arbitrary magnitude. Specifically, we consider the task of node classification. However, the challenge is that some nodes in the graph are controlled by the adversary that can perturb node features. Now, if we apply our graph neural network, we are propagating adversarial information through the graph, which can change the prediction for a target node. So we ask the question, how can we limit the propagation of such adversarial messages? We propose to exploit the underlying message passing principles and to intercept adversarial messages. And we implement that in two ways. On the one hand, we randomly delete edges in the graph, because by deleting edges, we disconnect potentially perturbed nodes from target nodes, which prevents the propagation of messages. On the other hand, we replace node features by a clean ablation token, which hides the underlying potentially adversarial information. In practice, we draw different graphs from our smoothing distribution, where we randomly delete edges and ablate nodes. Note that each of these graphs has a certain probability and that we use a graph neural network to classify the node in each of these graphs. So this yields a probability distribution over class labels. In the end, we construct a so-called smooth classifier that takes the majority vote among these predictions, which corresponds to the class with the largest probability mass in this distribution. To construct robustness certificates, we assume the worst case, that is, a single adversarial message is enough to change the prediction. We bound this probability to receive at least a single adversarial message, which is called delta. The idea is that delta bounds the probability mass in this distribution that is controlled by the worst case adversary. If the adversary does not control enough probability mass to change the majority class, as we can see in this figure, then we can issue robustness certificates for our smooth classifier. Experimentally, we obtain certificates against strong adversaries that control multiple nodes in the graph. On the x-axis, you see the number of perturbed nodes, and on the y-axis, the certified accuracy, meaning the ratio of nodes that are correctly classified and certifiable robust. We also divide the certifiable radius by the receptive field size to better incorporate how much percentage of the receptive fields we can certify. Interestingly, we can issue stronger certificates against nodes that are more distant to the target node. We also show that graph sparsification improves certifiable robustness, because on the one hand, sparsification reduces the messages to intercept, and on the other hand, it reduces the receptive field size, meaning the number of nodes that could be compromised by the adversary. With interception smoothing, for the first time we can certify robustness against strong adversaries that control multiple nodes in the graph and perturb node features by an arbitrary magnitude. This is in contrast to existing certificates that can only certify a few attribute changes all over the graph. For example, if each node had just a single feature, then we could certify many nodes with such certificates. However, in practice, nodes usually have a high feature dimensionality, so such certificates do not really work to certify entire nodes. The exciting part about our certificates is that they are completely independent of how high dimensional the underlying node data might be. Our method is also efficient. For example, we can compute certificates on CoreML within just 17 seconds. The main reason is that we only need 300 Monte Carlo samples to obtain valid certificates. This is in contrast to existing smoothing certificates for graph neural networks that use up to 1 million Monte Carlo samples. Overall, we propose gray box certificates for graph neural networks that exploit the underlying message passing principles. We can certify robustness against much stronger adversaries that control multiple nodes in the graph and perturb node features by an arbitrary magnitude. Our certificates are not just model agnostic, they are also efficient. Thank you.